we've completed the study of carbonyl compounds with the use of the thiazolium salts to couple two aldehydes together. And that was the material for the first exam was over. We now move into the second unit of the organic chemistry class, second semester, and that is to talk about conjugated systems. And we begin by reviewing some of the unique properties of allylic systems. And the allylic position is the position adjacent to a carbon-carbon pi-bond. So not on the alkene, but next to the alkene. One thing we note is that the bond dissociation energy for the allylic carbon-hydrogen bond is approximately 87 kilocalories per mole, which is less than any of the usual sp3CH bonds, which for the primary was approximately 101 kilocalories per mole. For the secondary was approximately 98.5 kilocalories per mole. And for the tertiary was approximately 96.5 kilocalories per mole on average. The implication being that since this carbon-hydrogen bond is weaker than any of these, that the resulting allylic radical is more stable even than a tertiary radical. If we look at the corresponding alkyl bromide, it undergoes salicylisis, or heating with aquatic solvent like methanol. The rate approximately equal to that of a secondary alkyl halide. Implying that a carbocation is formed, even though it's a primary allylic position. Because we see that this undergoes an SN1 pathway with a rate that doesn't depend on the nucleophile concentration. And it implies that the stability of this carbocation is approximately equal to the stability of an ordinary secondary carbocation. Not as stable as the radical, but still quite stable. Third observation is that the pKa of the allylic hydrogen is approximately 40, which is 10 orders of magnitude greater acidity than an ordinary sp3CH bond. And that implies that the allylic anion has some special stability. methyl anion. You can also observe that if we compare the rate of reaction of the allylic chloride, to the rate of reaction for regular orbital chloride, or 1-chloropropane, towards reaction with iodine at 50 degrees C, Finkelstein reaction, that the rate of the reaction of allyl chloride is 73 times the rate of the reaction of propyl chloride. So the SN2 reaction is also much faster at the allyl position. In addition to the SN1 reaction being faster at the allyl position, because a primary alloalkane usually has a negligible rate of unimolecular substitution. We also know that allylic alcohols can be oxidized under much milder conditions than ordinary alcohols, using manganese 4 oxide instead of the chromium 6 reagent to generate the corresponding alcohol, whereas this condition will not oxidize ordinary alcohols. So there are a number of things about that allylic position that are different from standard alkyl groups. The adjacent pi bond is having an effect on the stability of the radical, the stability of the carbocation, the stability of the anion, the transition state for the SN2 reaction, as well as the reactivity with oxidizing agents. We can explain this with resonance because the adjacent pi bond allows us to write a resonance structure that moves the radical for the carbocation or the carbanion onto the other end of the molecule. A resonance stabilized anion is going to be more stable than an anion that's not stabilized by resonance. A resonance stabilized carbocation that spreads that positive charge out over 2 carbons is going to be more stable than an ordinary carbocation. We know that hyperconjugation stabilizes carbocations. Resonance stabilizes them even more. And a resonance stabilized radical is going to be more stable than a radical for the same reason, hyperconjugation stabilizes. We've already shown the transition state for the SN2 reaction with the adjacent pi bond contributing. But to really understand the chemistry of these allylic positions and what it is that causes that resonance stabilized allylic anion or cation or radical to be more stable, we need to look in more detail at the atomic orbitals that are involved in forming the molecular orbitals for the extended pi system. So we can't avoid molecular orbital theory. For extended pi systems, if we want to understand all of the chemistry of the extension pi systems, not just for the allyl material, but for conjugated systems such as 1,3-butadiene, where we have 2 pi bonds adjacent to each other, or conjugated systems like benzene, where we have a 6-membered ring with 3 double bonds, or longer conjugated systems like 1,3,5-hexatriene. Fortunately, in order to understand the chemistry of the extended pi system, we don't need to consider the sigma orbitals, the in-plane orbitals. This is a planar molecule. I'm going to write it as the carbocation. We can write it as the radical or the carbanion as well. It's a planar molecule. It's C3H5, which means that the total number of molecular orbitals is 3 times 4 plus 5, or 17. Total molecular orbitals, because each carbon brings with it a 2s, a 2px, a 2py, and a 2pz orbital, and each hydrogen brings with it just a single 1s orbital. And we know that the total number of molecular orbitals in a system is always equal to the total number of atomic orbitals that they're formed from. So if we start with 17 atomic orbitals, we will have 17 total molecular orbitals. But since this is a planar molecule, if we look at the plane of the molecule as the xy plane, the 2s, the 2px, and the 2py orbitals, and all of the 1s orbitals lie in the plane. So the pi system is created only from the 2pz orbitals. Those are the only orbitals that are not in the plane of the molecule, and there are only 3 of them. Therefore, there are only 3 high symmetry molecular orbitals. It's going to be a whole lot easier to think about how to form 3 total molecular orbitals than how to form 17 total molecular orbitals. For 1,3-butadiene, there are 4 high symmetry orbitals. For 1,3,5-hexatriene, there are 6. So the number of pi orbitals is much smaller than the total number of orbitals. The total number of orbitals here would be 6 times 4 plus the 10 hydrogens, sorry, the 8 hydrogens, which would be 24 plus 8, or 32 total MOs. Fortunately, we're only going to have to worry about what 6 of those look like. And that's going to make our lives a whole heck of a lot easier. So how do we form a pi system, pi molecular orbitals, from p orbitals? Let's go back and review what ethene looks like in terms of its molecular orbitals. And let's use valence bond theory, because valence bond theory is a much easier method for looking at the sigma framework than is molecular orbital theory. And since we're not really interested in the sigma framework anyway, we're only going to be worried about the pi system. The pi system is identical in molecular orbital theory and valence bond theory. So we can use the simpler model and still get the results we need. So normally by valence bond theory, we would say that these are trivial planar. Carbon, electronic geometry, and that would mean that they are sp2 hybrids. We would have 3 sp2 hybrid orbitals then on the carbon with bond angles of approximately 120 degrees. And the carbon-carbon sigma bond would be formed by the overlap of one of those sp2 orbitals with the other sp2 orbital, and the carbon-hydrogen sigma bonds would be formed by the overlap of an sp2 hybrid orbital on carbon and a 1s orbital on hydrogen. So we would have 4 identical sp2 to 1s sigma bonds, the 4 carbon-hydrogen bonds, and we would have 2 sp2 orbitals pointing at each other to form a sigma frame, a sigma bond between the 2 carbons. And we would then have left on the carbons an out of plane p orbital, z, that's not used in the sigma bonding. These pz orbitals would then overlap if I rotate this molecule so that the board is now the yz plane instead of the xy plane. I would get an orbital formed from constructive overlap between the 2 carbons. That looks like that. This is a pi bonding orbital. And then I would also get the corresponding orbital resulting from destructive overlap, where a new node will be formed, which is the pi anti-bonding orbital. Where the sign on the wave function is different on the 2 carbons. So I form a pi bonding and a pi star, or anti-bonding orbital. The 2 electrons go into the pi bonding orbital, and the anti-bonding orbital is empty. And that stabilizes the system by allowing the 2 electrons to lower their energy from where they were in the original p orbitals. And if we wanted to look at that on an energy diagram, we would start with our 2 pz orbitals here, and we would have the pi bonding orbital lower in energy and the pi star orbital rising in energy by the same amount. And the 2 electrons would then pair up in the pi orbital because the gap, the distance between these 2, is much larger than the spin pairing energy that's required to flip one spin from the alpha state to the beta state, or from the +1/2 state to the -1/2 state. So the pi system is more stable. Generally, in the valence bond theory, we don't worry a whole lot about the anti-bonding orbitals because they're empty anyway. We worry primarily about the bonding orbital. But one of the rules of molecular orbital theory is that the sum of the energies of molecular orbitals has to be equal to the sum of the energies of the atomic orbitals. have to have the same number of molecular orbitals as you have atomic orbitals, and the sum of their energies has to be identical. The molecule is more stable than the atoms individually because the bonding orbitals are filled and the anti-bonding orbitals are empty. If you were to fill the anti-bonding orbitals, then there would be no bonds formed, the bond order would become 0, and the molecule would be unstable and would go apart. And that's why we don't have a helium dimer. We have hydrogen diatomic because we have 2 bonding electrons and no anti-bonding electrons. But helium is a monoatomic because there are 4 electrons and actually fill both the bonding and the anti-bonding orbitals and result in a bonding order of 0. So all we need to do is we need to extend what we've just done here, combining 2 pz orbitals with one another to form a bonding orbital and anti-bonding orbital, to combining more than 2 pz orbitals for the longer system. And that shouldn't be too terrible. Another rule of molecular orbital theory that will become relevant when we move into some additional reactions is that orbitals may only combine with other orbitals of identical symmetry. And that's why the pz orbitals don't combine with any of the other orbitals that are in plane, because the other orbitals don't have the same symmetry as the pz. The pz orbital has a node in the xy plane. It's the only orbital that has a node in the xy plane. The s orbital has no nodes. Well, the 2s orbital has a spherical node, but no angular nodes. And the px and py orbitals have nodes in the yz plane and the xz plane, respectively. But that's not the same as having a node in the xy plane. So in all of these cases, we're going to be thinking about a molecule in the xy plane and the outer plane orbitals have an xy node at z equals 0, right, which defines the xy plane, and those will form the pi system. So in this case, we have 3 pz orbitals. We have a pz orbital on this carbon. We have a pz orbital on the center carbon. We have a pz orbital on the end carbon. The circle positive plus sign here is the positive charge. And the plus and minus signs within below are the sign on the wave function psi from which the orbital was generated. And if you remember, the orbital kind of looks like this, where it's got a node at the nucleus and positive sign on the wave function in one direction and negative sign on the wave function in the other direction. And then when we square it, we make a radial probability function. It looks like this. And these two swept into 3 dimensions are what create these 2 lobes in the dumbbell-shaped orbital. So we're going to take these 3 pz orbitals and we're going to make from it 3 high symmetry molecular orbitals. on an energy diagram. So we have our three half-filled PZ orbitals here in the center, and we know that the three pi symmetry molecular orbitals that we make have to add up to the same energy as those three. So how are we going to do this? Well, the simplest thing to do is always what I've shown there, which is to take your three PZ orbitals and interact them constructively so that the electron can spread over the entire molecule. So we get a big lobe extending over three carbons in the top and extending over the three carbons in the bottom. That's going to lower the energy because the electron likes to be able to spread out over three nuclei. In fact, it likes to be able to spread over three nuclei better than it likes to be able to spread over two nuclei. So this pi bonding orbital is going to be lower in energy than the pi bonding orbital from the regular alkene. So if we put this on the energy diagram, this orbital is going to be down here somewhere. So my original P orbital is here. My bonding orbital is down below. Right now, we're not letting the electrons play. Those electrons are in a box somewhere waiting for us to form the molecular orbitals, and then we'll worry about where they're put. And actually, since we're working with the cation, it only has 2 electrons in it. There's no third electron in the pi system because the p orbital on this one is empty. The other way, right, that would be obvious would be to put everything out of phase in which case we're going to make 2 new nodes, and the orbital will be antibonding with respect to both of the carbon-carbon bonds. And we'd annihilate some of the volume. We get a little asymmetry here. We've got 2 new nodes, that's anti-bonding. Its energy will be up here somewhere. The third way we can interact these is to have a node going straight through the center, which actually goes through the middle carbon, meaning that the p orbital from that carbon makes no contribution to this molecular orbital. And that molecular orbital has 1 new node. And has electron density that can only be on the 2 outer atoms and not on the center atom. There's no net bonding or net anti-bonding interaction here because these 2 atoms are too far apart, and this atom is not making a contribution. So that orbital is what we call a non-bonding orbital. And its energy is identical to the energy of the p orbitals from which it was formed. The bonding orbital is lower in energy than the orbitals that formed it. The non-bonding orbital is identical in energy to the orbitals that formed it. And the anti-bonding orbital is higher in energy. we have three new orbitals, one of which has dropped in energy, one of which has not changed in energy, and one of which has risen in energy, and the energy gap between the bonding pi and the non-bonding pi orbital has to be identical to the energy gap between the anti-bonding pi and the non-bonding pi orbital, so that the sum of these three energies is equal to the sum of the three energies. When we have an odd number of carbon atoms, as we do in this situation, there is always going to be a node going right through the carbon atom. So the PZ on the center carbon does not contribute to pi 2. And we can number these pi 1, pi 2, and pi 3 in order of increasing energy. So let's look at what the orbital energy diagram for the Allylic system would look like for the cation, for the radical, for the anion. The orbital system does not care how many electrons there are in it. In all three cases, it's being formed from the same atomic orbitals. So it's going to form a bonding orbital, pi 1, a non-bonding orbital, pi 2, and an anti-bonding orbital, pi 3. And pi 2 is going to be at the original energy level for a non-bonding orbital. The cation has 2 pi electrons, and they will both go into pi 1. The radical has 3 pi electrons, 2 in the pi bond and the 1 there, so the extra electron will go into pi 2, and the anion has 4 pi electrons. So pi 1 and pi 2 will both be filled. The highest occupied molecular orbital for the anion is pi 2. And that's the orbital that's going to matter, because this acts as a nucleophile. And for a nucleophile, the highest occupied molecular orbital is the reactive orbital. Because if a species is going to donate electrons, it's going to donate the highest energy electrons it has. For the radical, obviously the unpaired electron is the reactive orbital. And again, that's pi 2. The HOMO, the highest occupied molecular orbital for the cation is pi 1. But since pi 1, or since the cation is an electrophile, which is going to accept electrons, the reactive orbital is going to be the lowest unoccupied molecular orbital. Because if you're going to donate electrons to a system, you're going to put those electrons into the lowest energy power control available to you. That's the Aufbau principle, what caused us to put the first 2 electrons into pi 1 in the first place. So you'll notice that the reactive orbital is always pi 2, because it's the LUMO for the catalytic species, the radical for the unpaired electron, species with the unpaired electron, and the HOMO for the negatively charged species, because this is donating electrons, and this one is accepting electrons, and this one is trying to desperately compare its electrons. So pi 2 which is the orbital that has no electron density on the center carbon, is the reactive orbital. And that explains why an allylic system reacts only at the two ends of the system and never on the central carbon. And it's consistent with the resonance picture, because the resonance structure that we drew never had the negative charge on the center carbon. It only had the negative charge on carbon 1 and carbon 3. That's consistent with the orbital having electron density only on carbon 1 and carbon 3, because pi2 is the reactive orbital. This same method can be extended and will be extended to a longer chain pi system.